Hello. My name is Alexis Martinez, and today I will be presenting my DLT architecture design project on digital identity for my MS 514 class. The rationale for choosing the digital identity system using DLT or distributed ledger technology lies in addressing critical shortcomings in traditional identity management systems. First off, identity management solutions identify, authenticate, and authorize users to access services while prohibiting unauthorized users from access. Decentralized IDs, or DIDs, also known as decentralized identifiers, are digital IDs where individual identifiers are replaced with self-owned IDs stored on the blockchain, and their associate data is stored on personal devices. You can create your own DID or have a DID provider. Then, for verification, you turn to issuers to provide claims against it. Unlike traditional IDs, DIDs are not stored in the databases of vendors or organizations. Therefore, they are less vulnerable to data breaches or theft. These DIDs have numerous use cases, such as enabling credible and privacy customers KYC, e-voting, tax payments, and event check-ins. Next, we look at the vulnerability of centralized systems. Traditional identity management systems such as banks, governments, and corporations have a centralized control structure which introduces a single point of failure. Breaches such as the Bank of America hack in 2024 exposed personal data of over 57,000 customers, demonstrating the vulnerabilities of centralized databases to external attacks. In traditional systems, third-party organizations have control over user data and often share or misuse personal information without explicit user consent. Identity fraud, data breaches, and unauthorized access are rampant in centralized systems. Since all user data is stored in a central database, hackers often target these systems. Existing centralized systems, while fast, lack scalability and security, and the current centralized identity systems are difficult to scale for national or global usage without introducing major security risks. Next, looking at the benefits of DLT for identity management, we have a decentralized system using DLT eliminates the central authority distributing control across multiple nodes, which makes the system more secure and reduces the likelihood of breaches. Users maintain ownership and control of their identity data rather than entrusting it to a centralized entity. A DLT-based identity system allows for self-sovereign identities, meaning that individuals fully control their identity and personal information. The systems use decentralized identifiers, DIDs, and verifiable credentials stored off-chain for privacy, ensuring that users can selectively share specific identity attributes without revealing the full personal details. DLT provides an immutable, tamper-proof record of identity data on the blockchain. Cryptographic proofs ensure that identity records cannot be altered, while smart contracts automate the verification process, creating a trustless environment that doesn't rely on intermediaries. DLT offers global interoperability through decentralized networks that can be scaled for international identity verification needs. Additionally, technologies like Hyperledger and Ethereum offer platforms that balance scalability without decentralization, supporting a wide range of applications for small businesses to national identity systems. The DLT-based architecture leverages technology like zero-knowledge proofs and layer 2 scaling solutions. Now onto our proposed architecture. The architecture design focuses on creating a decentralized identity management system using a DLT platform such as Hyperledger Indy. The key components of the design include blockchain and decentralized identifiers, verifiable credentials, smart contract, user wallets, identity verifiers, and encrypted storage for verifiable credentials, distributed ledgers, and cryptographic proofs. So the blockchain of the system is used to store decentralized identifiers. It ensures that identity records are immutable and verifiable without relying on central authority. Decentralized identifiers are unique identifiers that are stored on the blockchain. They allow individuals to prove their identity without relying on centralized databases. Verifiable credentials are the identities documents issued by trusted entities, such as driver's license or university degrees. These credentials are cryptographically signed and stored off-chain, but references and proofs of them are maintained on-chain. Smart contracts are to manage interactions between users and identity verifiers. They ensure the verifications are automated and trustless, requiring no intermediary to validate the credentials. User wallets. These will allow individuals to store their DIDs and verifiable credentials. Users can share the credentials with third parties to verify the identity in a decentralized manner. The distributed ledger is, of course, the blockchain, and the cryptographic proofs are the mathematical evidence that verifies the authenticity of identity data without exposing the actual credentials. And these components consist of identity issuers, identity verifiers, and off-chain storage credentials. Now for the architectural challenges. Our first challenge is scalability. One of the key issues with DLT systems, particularly public blockchains like Ethereum or even permissioned blockchains like Hyperledger Indy, is scalability. As the number of users grow, the system needs to handle a large number of identity-related transactions, which can overload the blockchain. Integration with legacy systems is another challenge, and that's where existing identity management infrastructures are centralized and do not natively support decentralized technologies. Integrating these systems with DLT-based identity systems requires significant effort and adaptation. For privacy versus transparency, the challenge is inherent in blockchain when they can conflict with the need. Blockchain's inherent transparency can conflict with the need for user privacy in identity systems. While blockchain provides immutability and transparency, it is crucial to ensure that sensitive personal information is not exposed or stored publicly. Data storage and management. For data storage and management, storing verifiable credentials off-chain introduces challenges around data management, encryption standards, and ensuring that credentials are accessible and secure without compromising privacy. Next, we have energy consumption. Depending on the DLT platform used, energy consumption can become a concern. Systems that rely on proof of work require significant computational power and energy resources to process and validate transactions. Now on to how DLT is solving these problems. For our architectural challenges, it actually already has built-in solutions. In this slide, we touch on potential solutions for the challenges listed previously. So for scalability, implementing layer 2 solutions to handle transactions off the main blockchain could improve scalability by reducing the load on the main ledger. For integration with the legacy system, the potential solution is to develop interoperability protocols, and offering incremental integration could help bridges and gaps between centralized legacy systems and decentralized DLT systems. For privacy versus transparency solutions, using zero-knowledge proofs or other cryptographic techniques ensure privacy while still providing verifiability. This allows the system to prove certain facts without revealing the actual data. Data storage and management solutions would be potential solutions for data storage and management would be strong encryption techniques, robust access control mechanisms, and ensuring compatibility between off-chain storage providers, and the blockchain will mitigate the challenge. For energy consumption, the potential solution is transitioning to more energy efficient consensus mechanisms such as proof of stake or adopting permissioned blockchains that do not require resources. So for the problem DLT is solving itself, DLT addresses the key issues of centralization and security. It decentralizes control by distributing data across multiple nodes, meaning there is no single point of failure. Each user holds their own identity, and no one entity has complete control over the data. DLT also enhances security and privacy. It provides cryptographic protections, ensuring that users' identities are secure and that personal information isn't exposed unnecessarily. At that same time, users have full control over their data, deciding when and how it is shared. In summary, DLT is solving the problem of vulnerability to breaches, privacy concerns, and central points of failure by decentralizing identity management, thereby offering user-controlled identities with enhanced security and privacy. How the architecture solves the problem. First, we have decentralized control. By using decentralized identifiers or DIDs, the architecture allows users to control their own identity data. without relying on the central authority. This reduces risks associated with data breaches and centralized points of failure, as control is distributed across decentralized networks. Second, we leverage the immutability of blockchain technology. This means that once identity credentials are recorded on the blockchain, they cannot be tampered with. The blockchain provides an unchangeable, verifiable record of identity data, ensuring security and trust in the system. Finally, architecture ensures privacy protection. Users can selectively share specific credentials without revealing their identity. For example, they can prove their age of citizenship without sharing their full name or other personal details, thereby minimizing unnecessary data exposures. To further enhance the efficiency and scalability of our digital identity system, we propose a few architectural changes. First, we plan to implement layer 2 solutions such as state channels and sidechains. These are designed to handle transactions off the main blockchain, significantly improving scalability, while maintaining the security and decentralization benefits of DLT. This is especially crucial when dealing with the large volumes of identity verifications. Next, we'll explore zero-knowledge proofs. This technology allows for privacy preserving identity verification. With zero-knowledge proofs, users can prove that they possess valid credentials without revealing the actual data, helping reduce blockchain bloat while enhancing privacy. Next, we'll explore zero-knowledge proof. This technology allows for privacy preserving identity verification. With zero-knowledge proof, users can prove that they possess valid credentials without revealing the actual data, helping reduce blockchain bloat while enhancing privacy. Finally, the architectural diagram on the next slide illustrate how these layer 2 solutions will integrate into our system, allowing for scalability and efficiency, digital identity management while still upholding the core principle of privacy and security. In conclusion, DLT-based digital identity systems provide a robust solution to the challenges we face in traditional identity management. By decentralizing control, these systems enhance both privacy and security, ensuring that users maintain ownership of their personal data. Furthermore, with ongoing advancements in blockchain technology, such as a layer 2 scaling solution and zero-knowledge proof, we can expect these systems to become more efficient and scalable, making them viable for broader adoption across industries and even on a global scale. Thank you for your time and attention. And here are my sources.